Hello.
Hello. Hello, Clara. How are you? Hello.
Hello.
Hello. Are you getting my voice?
Yeah. Alrighty.
Yeah. How are you?
Good. How are you?
Yeah, I'm good. Do you have any doubt from last classes?
No, it's all good.
Okay. Let me share my screen. Okay. Today we will start with from satellite communication, right?
Mm-hmm.
We did cover the link design and all those topics. So today we will start the topic from page number 55 of its slide one.
Just a second. That slide. Which
Page number page number 14, slide 55 of your notes one.
that's link design too, right?
Yeah, communication satellite. Are you seeing it?
Just a second. Oh yeah. Okay.
Okay.
Yeah.
Okay, let's start. So, these are the satellite communication we will be studying. In satellite, what happens that we have two Earth system, and we have a satellite system here in cloud. Here the signal are being sent from Earth station to satellite, that is known as uplink at uplink frequency. And here the signal are being these uplink frequency are translated to some another frequency with the help of the transponder and all those things, and we will be getting downlink frequency. This way satellite communication is working. Okay, so basically this is the mode of this is the funda behind the communication using satellite. Okay, so how to place a satellite in such a orbit so that we will give a signal, and we will send the signal from Earth station at the transmitter, one Earth station transmitter and one Earth station receiver, and it can be maximum usable to us. So on that basis, we are placing different satellite in different orbit. We have low Earth orbit, we have medium Earth orbit, and we have geo orbit. Okay,
Mhm.
so the satellite that are placed in geostationary orbit, okay, geo orbit is known as geosatellite. Okay, and at this and at this and this is 36,000 kilometer above from equator. In this we have a geostationary orbit.
Mhm.
Geostationary orbit or geo-equatorial orbit. Other name is that. Okay. At this orbit, why we are placing the satellite at this orbit? Because the Earth is rotating, and this satellite is also rotating with the same speed of the Earth. So this satellite appears to be stationary when we view from Earth. Okay, so this is known as geostationary orbit, and these are placed from 36,000 kilometers from the Earth. So what are being advantages of these of satellite being placed at geo orbit? There are a lot of advantages. Since these satellite can be viewed, can be always view from the Earth, so we can have the communication throughout the day, or throughout a year, or every time we can have the communication. And also, since it is placed at very large distance from the Earth, so at very large distance from the equator, so it can cover every point or large point of the Earth's surface. Only few points at the northern or southern hemisphere it is not able to cover. But except that 95% of the part of the Earth can be communicated with the help of this geostationary orbit. Okay,
Mhm.
it has a very, but the apart from advantage, this had disadvantage that it has a very long path. Okay, very long path, and we studied that our path loss is 4 pi by d by lambda squared. So so path loss will be very high. Path loss will very high in this satellite. Okay, okay.
Mhm.
This is the geostationary orbit, and the satellite known as geostationary satellite or geosynchronous satellite. Okay, now coming to the point, how the satellite communication are working here. Satellite communication from the earth station, from transmitter, and another earth station we have receiver. The satellite, the transmitter are sending a signal to the satellite substation. This is satellite substation. Okay, and from here the signal are being transmitted back to the receiver. Okay, so what happens, now we will study this satellite subsystem. In our satellite subsystem, first block is low noise amplifier. After that we have transponder. Okay, after that we have a mixer, frequency shift, and all those gain path and power amplifier. Okay, and here this is uplink frequency, and we will get here the downlink frequency. Okay, downlink frequency. Uplink frequency is always higher than the downlink frequency. Okay, the frequency at which we are sending the signal, that is known as uplink frequency. This is uplink frequency, and the frequency at which we are downloading the signal, that is downlink frequency. Okay, these are the important thing here. Here we have the transponder that are responsible for converting this uplink to the downlink frequency. Important thing is that uplink is always greater than downlink. Okay,
Mhm.
okay, do you have any doubt here?
No.
Can you see page number 57, slide 57 of page 15?
57. Yeah.
Okay, you can see we have a figure, right?
Mm-hmm.
Okay, this is the Earth surface of the elevation angle for a receiver on Earth. Okay, so you
Mm-hmm.
can see for different elevation angle, we have different power. Okay, so basically what does it saying that if we are placing a satellite at different elevation angle, okay, at different elevation, then our power that being used is also different at everywhere. You can observe here that once our elevation angle 0 degree is the equator, okay, and once we are going from the equator from 0 degree to far, okay, from 0 degree to far, you can see that we have a different power that being observed.
Mm-hmm.
Here we have this is here we have uplink frequency of 14 gigahertz and downlink frequency of 11 gigahertz. Okay, so basically what does it saying that once we are going away from the equator, you can observe that the power that being taken or that being calculated is always decreasing,
Mm-hmm.
because you can observe from the equation that P is inversely proportional to distance. Are you getting me? When you can see, are you able to visualize in this figure? When you are going away from the equator, your distance are being increased and are your power is decreasing. Are you getting this one
Mm-hmm.
from the figure?
Yeah.
Are you able to observe it? 0 degree is the equator. Okay.
Mm-hmm.
Okay, so this example are showing this one. Yeah, are you getting me?
Mm-hmm.
Okay. Okay, and you can observe the same thing. You can observe the same thing, and that EIRP calculation they did. Okay, EIRP calculation they did for the different, and they have given you the path losses and all those things. Are you getting it?
Mm-hmm.
Are you getting those tables and all those things? If you have any
Yeah.
doubt, or you can observe for some time. Okay, and also you can observe that we are as as we are uh, coming our receiver power is getting reduced, received signal
Mm-hmm.
power. You can see that when our typical path loss is 39,000 kilometer at 11 gigahertz, we have more path loss. Okay,
Mm-hmm.
I think this is self explained from the blocks and all those things. Do you have anything to ask here? Please go through page number 57, 58, 59, and 60. If you have any doubt, then ask me.
Oh,
For 2 minutes
okay.
at least, go through those points.
Okay.
Okay. If these datas will be given, you can calculate all those things, right?
Mm-hmm.
Do you have any doubt? Then ask me.
Okay.
Okay. Can we go ahead?
Mm-hmm.
Can we go ahead? Can we?
Yes.
Okay.
Yes.
Now, one thing here that suppose what is our important thing? Signal to noise ratio. Okay. Signal to noise ratio. What do you mean by signal to noise ratio? Okay. SNR. Suppose ideally what it should be. It should be as higher as possible, right?
Mm-hmm.
Right or wrong?
Uh,
Signal to noise
mm,
ratio. If noise
high
is
as
will be
possible.
more, this ratio will be less. If noise will be less, this ratio will be more. Okay, so this ratio should be as good as possible. Okay, signal to noise
Mm-hmm.
ratio. So our intention how to improve signal to noise ratio. Okay, so that we can have a good signal. Suppose your
Mm-hmm.
noise is very high and your signal to noise ratio is very low. What does this mean? It will means that your signal is not detectable. You can't detect the signal since your noise is very high. Okay,
Yeah.
understood. So our intention in any type of communication is to increase signal to noise ratio. Okay,
Mm-hmm. Yeah.
to increase signal to noise ratio. Okay, how to improve signal to noise ratio? How we can improve the signal to noise ratio? We can use higher transmitter power. Okay, if we have high transmit power, we can have more signal. Okay, need more electrical power input to the transformer, large solar panel, or fewer transponder. Okay, this is our satellite. Okay, suppose this is our satellite. Okay, and we are giving some power from here, PT. Okay, so it basically telling that we will use high transmit power. Okay, transmit power. This one. Suppose this is our satellite. It will be getting some power. Okay, and it will be deliver this some. It will transmit some power to the receiver. So they are telling that our transmission power from the satellite to receiver should be as higher as possible. Okay, for making transmitter
Mm-hmm.
power higher, we can have large solar panel. Okay, large solar panel, so that solar panel will increase our PT from satellite, and our signal to noise ratio at the receiver will get increased. Okay, or use a transmit antenna, or we can use an antenna here. We can use a antenna here of higher gain. Second thing is that use antenna because our PR receiver power, if you remember, is PTGT and something. If we can increase this PT transmitted power, or we can increase this GT, then our signal received at the receiver will automatically will get increased. Okay, what do you mean by having the higher gain antenna? It means that our signal should be narrow width. Okay, narrow beam means that it should focusing to our destination only. It should focus to our destination only. Okay, so antenna will be so we can have a good antenna gain. Okay, so in this way we can improve either from increasing transmitted power, or we can increase the higher transmitted antenna gain. Apart from that, we have Another thing is that AE, okay, and AE aperture area is directly proportional to lambda square into 4 pi into gain of the receiver. Okay, if we can increase the gain of the receiver, we can increase the effective area also. We can increase the effective area. So another way to improving signal to noise ratio is to use a receiver antenna with higher gain. It means that larger effective aperture or also a physical larger. So these always increase the thing and reduce the noise power in the receiver. We can also go for some devices that have the lesser noise. Okay, that have the lesser noise. So these 3-4 things are parameter to increase the signal to noise ratio. Okay. First point is that we should have a higher transmit power. Okay, higher gain of transmission antenna, higher aperture area of the antenna at the receiver, and less noisy device. Okay, these are the things that we are looking in our satellite to improve our signal to noise ratio. Okay, any doubt till now?
No.
No.
Yes.
Okay, good. Then we will move to our another unit, non-linear system in wireless system. Okay, in wireless system we will go to the non-linear system topic. Okay. Why we need, first of all, question arises why we need linear system, why we need LTI system, linear time invariant system. We need linear system so that whatever input that we are sending to our device, we will get the input in a linear way. It means that we will get the same type of input. If we will have a linear system, our signal will not get distorted. Okay, our system output will be directly proportional to the input. There will be no any distortion will be happen. Okay, slope of, you can observe here. Suppose this is a system with gain G and you are sending a V input signal and you are getting V output. Okay. So what does, if a system of our is linear, suppose this is a linear system. Okay, this is linear system. Then what will happen? This will be an input. Okay, and if our system is linear, you will get a similar type of output. Because your system is linear, your output signal will not get distorted. So that is the advantages of a system being linear. Okay, but linear system or LTI system, linear time invariant system, with time it is also not changing. So our system or our devices should be linear in nature as much as possible, but practically it is not happening. Practical, it does not happen that our system being always linear. So what we are so that's why we are studying the non-linear system and try to reduce the non-linearity as much as possible. So what we are doing to study a system, we studied the non-linear system parameter. And suppose if we want to compare two system and we want to tell which system is better, then we can compare its non-linearity features and we can tell that this system will be better or this system will not be better on the basis of their non-linearity parameter. There are many parameters that are judging the non-linearity that like 1 dB compression point, 3 dB intercept point, intermodulation products over modulation. There are many things that are judging the non-linearity of a system. Okay.
Yeah.
So before that, we can see that okay, this is linear time invariant system. Before that, we will study that in our LTI system, superposition implies, okay, if we are sending two signal, then those signal will get sum up at the output. Okay, if the input signal is the sum of two component, the output is the sum of the output. Output is also sum of for the output. Okay. Okay. Now here, okay. Now we will see the non-linear system, how the non-linear system will behave. You can see if our system is non-linear, we are getting the output in this form, distorted output. And here output is not proportional to the input voltage every time. Okay. This is the CV linearity. You can observe that we have a clipping of the signal and signal is being distorted. Okay, and new frequency suppose this is your sinusoidal signal. So sinusoidal signal has always one frequency component. Okay, but here you will have the multiple frequency component at different frequency. So these frequency component are undesirable to us. These extra frequency component are undesirable to us, and that are because of the nonlinearity system. Okay. Okay. You can see different pages, that page number 7 and all the 8 and all those things of this nonlinear one. You can have the different nonlinearity, and it will be given you different frequency component. Okay, different cases of the nonlinearity. Do you have any doubt in the nonlinearity system basic concept?
No.
Okay. Okay.
So good.
Okay. Okay, there is one. Okay, this is also a type of non-linear system. Okay. Okay. Now let's see. Now we will see the block diagram of a wireless transmitter. We'll have a modulator. This is your non-linear system. Okay. This is your wireless transmitter. Here we will have a power amplifier in transmitter. Okay. Power amplifier is to boost up the signal. Okay, because our output signal is not that much good. So we are passing it through a power amplifier so that we will get a good output at the power at the output of the receiver. Okay. And these are our, we will have the mixer components are required for generating new frequency component and all those things. Okay. Okay, now we have a real amplifier behavior. Are you able to see the figure?
Amplifier.
Page number 11, 11/44, 54.
Just a second. Seven.
Page number 11/54.
Okay.
Are you able to see the figure?
Yeah.
Can you observe the figure? How this non-linearity? Can you observe the figure? You can see that how this non-linearity is happening. You can feel it. Go through the figure. Are you getting it? You can see we have an
The
input power
is
and
it
we have
the
a,
no,
sorry.
the output power changes?
Yeah, you can see that output power are being changes with the input power. Okay. In the AM system, what does mean by AM system? In the AM system, in the input power is the AM and output power is also in the AM. It means that output by input. And another system is AM and PM system, in which input power is input is the input power, and PM and out in the output you will be giving, you will be getting a phase shift. Okay, and in the output you will be getting a phase shift. Okay. Are you
Okay.
observing it?
Yeah.
Okay. Do you have anything to ask here?
How do we see that phase shift?
Yeah. I'm telling that, see, on your y-axis, they are telling that output power in dBm, or otherwise we have a phase shift in degree. Okay. You can you can see, are you seeing the dark star line, AM, PM, right?
Mm-hmm.
So there you can see that at different input power, you will be getting different phase shift. In the initial, around suppose minus at around minus 30, minus 13 dBm, I can, if I can assume that minus 13, around minus 13, you are getting around 0 degree phase shift, 0.5 or something like that. Okay, so that will be in degree. Okay, and around 5 dBm input power, you are getting around 5 degree of phase shift. Are you getting me?
Yeah.
Do you have any doubt?
No.
Okay.
Mhm.
In this way, you can observe your graph.
And how do we find this small signal gain
Okay.
on
For
page 12?
okay, for finding the small signal gain, okay, let's try to find the small signal gain. Okay, page number 12. Okay, .32 here, 30 here. Yeah, it can be around 29 dB. Okay, how to
And how
find?
do we
Do you have the answer?
no.
Okay, it can
How,
be if, sorry.
how do we read that? Like, what's the
Yeah,
small signal?
I am telling that what is gain? It is output by input, right?
Yeah.
It is output by input. So we can take one output, okay, and one input. You can observe at minus 10 dBm input power, you are getting around 19 dBm output power. Is it on? Are you getting or not? When your
So,
input power is minus 10 dBm,
mhm.
you are getting P output around plus 19 dBm, right or wrong?
Mhm.
Are you able to see it? At
Yeah.
around minus 10 dBm, you are getting around plus 19 dBm, because it
Yeah.
is little bit down than 20, right? I can assume it is 29, right? Can I assume it? As I can assume it 19, right? Okay.
So
Then what do you,
how is that?
sorry?
So you said that the gain is output over input.
Right, gain is output over input, and if we are calculating in dBm, that will be P output in dBm minus P input in dBm, right or wrong? Right or wrong? We studied
Um.
these things, right? Suppose you can see here, in generally, gain is P output by P input. Okay, when we find the gain in terms of log, okay, in terms of dB or dBm, then it will become, right, we can write it 10 log of 10 P output by 10 log 10 P input. Okay, so we can write it
Okay.
is in P output dBm or dB, dBm or dB, and P output dBm or dB, P input dBm and dB, right? And that will be P output dBm minus P input dBm. Agree or not? Not agree. Are you getting my point? Clara, are you getting my point?
No. Where did the minus come from? I don't know.
Yeah, that is when you are dividing, when you are taking the taking how can I tell you? When you are dividing some log term, Do you remember from your basic mathematics log xy, you can write log x minus log y? Are you remembering?
Yeah, but I just don't get why do we have to write it in log if it's already in dB? Like we don't. Why do we have?
Yeah. For I'm giving you formula that what is your gain? Your gain is in P output by P in, right?
Yeah,
Agree? And
yeah.
this gain is not in dB. It is in normal unitless term. This formula is for unitless term. Agree?
Okay.
Now, if you want to have it in dB, what you will do?
Yeah.
Agree or not agree?
Yeah.
And this you can write 10 log 10 P output by P input, and that will be equal to 10 log 10 P output and 10 log 10 P input, and this is P output in dB, dB or dBm. If you multiply by 10 raised to 3, it will be dBm, or it will be P output P input dBm. Are you getting my point?
Yeah.
For writing gain into dBm, you should have your formula is that P output minus P in. Are you getting me?
Yeah. I get it.
Got it or not got it? Okay. Any doubt?
No,
Any doubt, Clara?
no.
No? No, observe. Now observe. I'm taking 3 points. Okay. When our P input is minus dB, minus 10 dBm, you can get everything. When you gain out the linear. What is your P output? Can you tell me? For minus 10, tell me. For minus 5 dBm, tell me. And
19.
for 0 dBm, you tell me again.
So from -10, it's 19.
Yeah, we can tell it is around 19 dBm, right? For
Or
minus 5.
-5 is 25.
Yeah, 25 or less than 25, you can say. It is, if you zoom it is less than 25.
24.
Around minus 24, right? 24,
24.
right?
Mhm.
Right or wrong?
Yeah, it's right.
Right? Because they should give you the exact value. And for 0 dBm, how much it is?
30.
29. We can, because it is less than 30, we can tell it is 29, right?
Yeah.
Okay. And you can ask me why we are not taking input voltage outside that. Because till then, the graph is linear only. After that, graph is not linear. Are you observing it?
Okay, so I should just check for the linear
Yeah.
parts.
And here, what is the gain? You know, gain is P output minus P input. 19 minus this one. 24 minus this one. 29 minus 0. Everything you will get 29, right? Are you getting it?
Yeah.
Are you getting it, Clara, or not?
Yes, I'm getting
Okay. Understood how we found, right?
it. Yeah.
Okay. Okay, can you see the second question?
Mm-hmm.
At what input power does it become significant non-linear? Now you can give me answer.
At -1. Mhm.
Yeah, around -1, right? Right?
Am I just looking at the AM?
No. Yeah. AM. Because you are dealing in the gain only. If you
Yeah.
have to deal in the phase,
Okay.
you have to see the AM. Around -1 dBm, right? Is it?
Yeah. Yes.
Okay. Any doubt? Any more doubt?
No.
Do you have?
Mm-mm.
Okay. 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 Good. Good till now.
Yeah.
Okay. So that's why I'm going in the sequence of your paper, of your notes, so that we can understand that
Mm-hmm.
what is important. Okay. Now small signal model. Okay. See, we have a non-linear system. Okay.
Mm-hmm.
So what we are doing in a small signal model, for a small signal model, we are taking a part of a non-linear system where your system is linear.
Mm-hmm.
You can see this is your V out and this is your V in. Okay.
Mm-hmm.
This is your non-linear system. Okay. You can see, we can tell that our system can be can be linear. I can approximate till these points, right or wrong. Right
Yeah.
or wrong. So
Yeah.
at these points, if we are considering our signal non-linear, then we can have a small signal model of this linear, of this system. So what do you mean by small signal model? If you have a non-linear signal, we are taking a part of a small signal only, and we are studying that region, that is linear region, because our interest is in linear region only, right?
Mm-hmm.
So amplifier are often analyzed using a linear model called a small signal model, but this is valid only for a small signal. Are you getting me? Only for small signals, it is valid. When your input signal are very small. Okay. Input voltage range restricted to a value close to zero, where amplifier characteristics is approximately linear. Okay. For studying a small signal model, we are restricted to input voltages which are closer to zero, where the amplifier characteristics is approximate linear. Okay, are you got it? Are you getting it?
Yeah.
For large signal model, it should be non-linear model. Okay, for study large signal model, we have to study for study large signal model, we have to use non-linear model. Okay, got it?
Mm-hmm. Yeah.
Okay, any doubt?
No.
Okay. Memory-less model. What do you mean by memory-less model? Do you studied signal system?
Yeah.
So in our signal system, we have a many system like causal system, non-causal system, memory system, dynamic system. Are you remembering?
Yeah.
Memory-less system are those system whose outputs depends only on present input, not on the future or not on the past. Are you getting it?
Mm-hmm.
If you able to recall it, we had a causal system in which our output is depending upon present input and past and future input, and present input and past input. Okay, that is the causal system. And we have a non-causal system that output is depending upon present input and future input. Okay, but apart from that, we have a memory-less model in which our output is depending upon only on the present input. Okay, that is the memory-less model. Are you getting my point?
Mm-hmm.
Okay, so we can apply this memory-less model only to a linear system. Okay, so we will, so inside a linear region, we can characterize our equation that our V output is only the function of V in. Okay, that means that whatever is today's input is present, that will only give us the output. It do not have any storing element, something like that, so that it can tell you that we will have the output at the of the future or of the past. Okay, and this f function, wherever you will get this f function, it is a linear function. Linear or denote can be denoted by non-linear also. Memory-less model independent of time. As I told you, any memory-less system are independent of time. It do not depends upon independent. It can be linear or non-linear. Sorry. Memory-less system, it's independent of time. It do not depend upon any value of t. Okay. So its behavior is independent of frequency. Okay. So what do you mean by its behavior is independent of frequency? So when the frequency are being changed, his behavior is also not changing. Okay. It can model narrow band and good wideband amplifier. Okay. Understood. Any doubt till now, you can ask me. You can go through the slide one more time. If you have any doubt, you can ask me.
That's okay.
Okay. Very good. Now we have a polynomial memory-less model. Okay. Polynomial function, we have a V output. They have indicated V output in the form of V and V input, and they are denoting V output V1 V in likewise. Okay. It represents the characteristics as a polynomial with a set of coefficient Bn. Okay. So it is a polynomial memory-less model. Okay, there is nothing to state here. If you're able to see the slide 17 and 18, you can get to know that we will have a V output in terms of different harmonics of different n, and when our cos to the power is even and cos to the power n is odd, you have a different signals when n is even and n is odd. Okay, so many terms are multiples of input frequency for n2 cos n omega 2, and this can be grouped together. You can see we have a output at the DC components and harmonics. Are you getting it? Are you getting it, Clara? Okay. Do you have anything to ask? Okay. No. Then we have a narrow band system. In our wireless communication, wireless system, we are concentrated on narrow band system. What is narrow band? Narrow band means that the beam that we are sending is very narrow. Okay. The beam that we are sending are very narrow. As a typical wireless transmitter, you can see many RF systems are relatively narrow bandwidth. Okay, that is, signal bandwidth is small compared to center frequency. Suppose this is our operating frequency. Assume. What is narrow bandwidth means? Suppose this is F0, our operating frequency is 1 gigahertz. Okay, and you have your beam nearer to this one only. Okay, and bandwidth is BW. Okay, it means that if your F0 is very greater than your bandwidth, okay, very greater than your bandwidth, then that system you can tell that it is a narrow band system. Okay, what do you mean by narrow band system? If your signal bandwidth is small compared to your center frequency, that is known as narrow bandwidth system, narrow band system. Are you getting it? This is a narrow band system. Narrow band. Okay, narrow band means that your bandwidth is small compared to center frequency. Okay. For that, we could use a band limiter generator. We can't model with a memoryless model or follow with a okay. So we will have a DC and harmonic. Do not reach the final output. Only frequency near the desired frequency will get to the output of the system. That is only the fundamental component. Are you getting me? Because why we are studying narrowband system? Suppose in our narrowband system, in generally in our in our system, we have a multiple frequency, very large frequency, but we are studying narrowband system. It means that only desired frequency will reach the output. Because if you see the before slide, we'll have the different number of frequencies, many frequencies, odd frequencies, even frequencies, and many harmonics was there. But if you will study narrowband system, only desired frequency will reach to the output. Okay, and another frequency will not reach the output. Okay, that's why we are concentrating on the narrow band system. Okay, narrow band system is very important, or you can say that we are using this system in our wireless communication. Okay, assuming our sinusoidal input to amplifier, after filtering, we will get this one, and voltage gain, they have given you voltage gain. Because we will see, we will have a different thing, we will have a filter and all those things. If we will send input to amplifier as sinusoidal wave, we will have V output n equal to odd as n, and it will be bn a to the power n 1 by 2 raised to n, where it varies from n by n minus 2 cos omega t. Okay, and that and our then our voltage gain will be okay the V output by Vane, and that will be ZV, and it is combination of 0 to odd and bn a raised to n minus n 1 by 2 raised to n minus 1 n minus 2. This is our output signal that we are getting. Okay. Okay, so these are the gain depends upon signal amplitude A. Okay, that's not good, because are signal are not independent of to the power n. If n is increasing, our signal will get decreased. That is the drawback here. Okay, you can see the example of simple non-linear amplifier. Okay, with third order non-linearity. What do you mean by third order non-linearity? If you're telling that, if somebody is telling that your system is third order non-linearity, that means that you will have different terms from B0, you will have BV in. Okay, you will have B2 V in square, and you will have B3 V in cube. Okay, so you have the different components. This is three order nonlinearity, third order nonlinearity. Okay, if suppose somebody is telling that you have a two order nonlinearity, then it will be B0, B1 V in, and B2 V in square. That is second order nonlinearity. Second order nonlinearity, and this is third order nonlinearity. Okay, are you getting it?
Yeah.
Okay, any doubt?
No.
Do you want to extend for half an hour more, or do you want to stop here? What are you
Oh, yeah.
planning? Sorry?
Yeah, we can stay.
We can stop.
We can stay if we have to
Yeah,
go.
yeah, yeah. Yeah, we can stay for half an hour, right? Okay. So example of simple nonlinear amplifier. You can see here V output. You can see this is the nonlinear system graph. Okay. Depending on the different values, it is behaving in that way. Okay. In your exam, they can ask you, they can give one equation, okay, and they can give the coefficient value, and you have to draw the graph. Okay. That is the nonlinearity of the graph. Okay. Do you have anything to ask here?
No.
Because I'm not seeing anything that it becomes significant. Nonlinear. Okay. Yeah, to become significant. Nonlinear. 1 plus TV. Okay. We can see another, assuming our amplifier is followed by band pass filter and input is sinusoidal, then we will have a gain. It's okay. Hence, here we will have a three order amplifier, that is n equal to 3. We observe that we have a gain in our system n equal to 0 to n equal to odd and n equal to odd, 0 to odd, and we have gain bn a raised to n minus n to 2n and n minus 1. And for studying the nonlinearity of third order, if it is a three order system, if it is a three order system, if it is a three order system, then our GV will become, then our n will become 3 and our Z will become B1 3 by 4 B3 A square. Okay, that is our this one. Okay, now
Yeah.
you can see the amplifier characteristics. With the amplifier, if I will say you, we draw your output Kara. At 0, at 0.5, at 1, at 1.5, and at 2. Okay, what is our intention? And your original Kara will slightly deviate. Okay, will slightly deviate. Diagram shows ZV equal to 10 minus 0.6 AV square. 0.6 using example coefficient, using the coefficient that we shown here, that coefficient given was B equal to 0, B1 equal to 10, B2 equal to 0, and B3 equal to minus 0.8. Then our gain will become B1 10 plus 3 by 4, B3 is minus 0.8 and A square. So our gain will become 0.6 A square. And that we have plotted here. That is our gain. Okay. Now gain that is our amplifier. That is our that we have to plot. That we have to plot the gain compression. This was our initial input. These we have given input, and we are expecting our output amplitude with our input, and we are expecting output. Amplitude. But when we pass it to our system, our gain got compressed. You can see that with amplitude, you can see with 0 it would be given you 10. Okay, after that if you see at 1, initially it was giving you 10. Okay, it was giving you 10 till here 0.1. You can measure it, it is almost 10. Now it will get reduced slowly, and drastically will reduce once it is more. Okay, so these are the gain, voltage gain. Okay, this is the voltage gain you must be getting, and this is your input voltage. So you can observe here, we will have a gain compression here. That gain are automatically got reduced, are getting reduced. Okay, are you getting it? Then that in our nonlinear system, gain are reducing very significantly, and that is known as gain compression. Are you getting it? Or do you have any doubt?
No, it's okay.
Okay. Okay. We will study some of the more parameters here. Voltage gain. Sorry.
There any problems in this that we can do or something?
Yeah, that's why I'm going line by line,
Okay.
because so that we can whenever we can get the problems, we can solve it, right? And you have sent it this slide and one more slide. Apart from that, do you have anything
But
more to send?
I have. I will send.
Okay, okay, you can send it. Okay,
So the
so
last
that
thing I sent was number 5, is it?
last time you sent synthesizer, frequency synthesizer. That was your lecture notes too, right?
Frequency sentences, yeah. So
Yeah,
yeah.
that was
Okay,
your lecture number 2, right?
lecture number 2. Yeah.
Okay. Right. So you can, how many lectures notes are you having?
So I have another so about the transmitter and about noise.
Okay, you can send those also. Okay.
Yeah. Yeah.
Yeah, because my target is to, I think in next two class tomorrow we will take also 1.5 hour, and
Yeah.
and if possible we can have one class in next weekdays, so that my plan is that to complete these notes in coming two classes. Okay, 2 to 3 classes.
Okay.
Okay,
Yeah.
you have total 4 notes, right?
Just a sec. So, because we're probably still gonna have a bit more because we're still studying it,
Okay.
but
Okay. It means
for
that
now,
today, till today, today's date, you have a 4 notes, right?
yeah.
Okay. I have 2 notes only of you. You can send another two. Okay.
I think I already sent the transmitter. I see it's in the lecture notes too. So one of
Okay.
them
In the
might.
lecture number 2, you have only the transmitter, right?
I sent everything. I sent everything. Now I checked. In lecture notes too is everything that we've
Okay. In
done.
lecture number, in the notes 2 that you send it has everything, right?
Yeah, it has everything. Yeah.
Okay. Okay. And the rest part you yet to receive, right?
Yeah.
Okay. Okay. No issue. We can see here that voltage gain of a third amplifier, we saw 3 order amplifier, that is b1 plus 3 by 4 b3 a square. What is the input power? We know input power p input equal to a square 2 r in, and output power equal to what will be output? Gain equal to, see, gain equal to p output by p in. So what will be the output power? Output power will be gain into p in. That will be that will be we can write gv a square in place of a, right? 2r out. Okay. And output power gain, we can write output power gain z equal to p output by p output by p in, that is r in by r output into zv square. Okay, for a match system. Now I am telling you, I'm just giving a relation of match system. What is match system?
Mm-hmm.
What is match system? Match system means that your input and your output resistance are same. If your input and output resistance are same, the signal will not reflect, will not have the reflection. Okay, it will not reflect back. Suppose in your transmission theory, you might have studied, if your this z in and this zl are equal to z naught or something like that, if your input and output are getting matched, it means that no signal, there will be no reflection. All of the signal will get transmitted. So that's why we are studying match system. And when we see the match system, in our r output is equal to r input. So our power gain z equal to zv square. Are you getting it?
Mm-hmm.
Okay. When our power input z equal to zv square, okay, then what does it mean? Now, what is your power gain? That is zv square, b1, b3 by 3a square, that is our zv, that was our voltage gain. Okay, and that is equal to b1 square, 3 by 2, b1, b3 a square plus 9 by 16, b3 square a to the power 4. Okay,
Mm-hmm.
these I am getting, and we want this p input, and we can substitute a square here. A as a 2 RPN that we already already saw that our P input is this one. So we can write A square as a 2R in into P input, and A equal to under root 2R in and P input. Okay.
Mhm.
So we will have B1 square 3 by 2 and B1 B3 A square in place of B1 B3, and in place of A square we have R P in, and in place of, if I'll put, I will get this term. So our gain, if I'll put those coefficient, that is B0 was 0, B1 was 10, B2 equal to 0, and B3 equal to minus 0.8, we will see that our power gain is much compressed with input power. So what will happen if suppose your input power is very large, then the problem arises. If our input system are very large, then we can't have the infinite power. So that is our the drawback. Okay,
Mhm.
that is our, can't we write, can't go to, so we can't have in our this non-linearity, we can't have the gain calculation when our input power is very high. Stems for our finite pronoun. Okay, let's see. Okay, do you have any doubt till now? Anything to ask?
No.
Can you see there is a question in page number 28? Can you see that question?
Yeah. Yeah.
Can you answer that?
Mm, just a second.
Yeah, sure.
Mm, the input is the, oh, mm, what? But am I looking at the graph above, like the first or the second graph?
You have to, yeah, both of the graph will be helpful for you.
So I should,
Both of the graph will give, we should give you same answer. You should learn the question that what input power does it become significantly non-linear,
if it's
not
not
even non-linear, significantly very high non-linearity existing.
5,
No, it will be
no?
10. See, till 5 it will be linear, right?
Oh,
Okay.
significant. Okay.
After 5 to 10 it is non-linear, but not that much significant.
Yeah, 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 yeah.
Yeah, are you
Okay.
getting it?
Yeah,
So
yeah, yeah.
best answer will be 10 dBm, right? Suppose if the questions come that when it will become non-linear, then what you would be telling, it will be 5 dBm, right?
Mm,
Okay, understood? Any doubt?
no.
Okay, very good. Okay, you can see consequences of wireless system. Okay, we
Mhm.
have two more thing, then we can. So what is gain compression? These questions can come. Amplifier gain falls as the input power increases. Yeah, that's true. This is the behavior of most of the simple amplifier. That's true. For one cubical polynomial, need B1 and B3 is opposite sign, then your gain will compressed. Okay. So we see the polynomial system in VC, we have the different B0, B1, B2, and B3. If these coefficients values B1 and B3 are different in sign, then we will have an opposite sign, then we will have the gain compression. Okay. Narrow band system, single sinusoidal input. We will have the output is still sinusoidal, no visible distance. That's why we are studying narrow band system. In our narrow band system, we do not require many harmonics. We are having only one harmonics that are centered around center frequency, that is fundamental frequency. Now, with a modulated signal, phase modulation and frequency modulation are okay. Constant amplitude, so constant amplifier again, it's okay. But amplitude modulation and QAM, quadrature amplifier, etc., varying amplitude, so varying amplifier gain and modulation will be distorted. Are you getting me? That in our AM system or QAM, quadrature amplitude modulation and these modulation AM and QAM, we will be getting distorted signal. Okay, we will be getting distorted signal, but in FM and PM there is no issue. Why? Can you tell me? Why? Can you tell me?
I don't know.
Yeah, because in our AM and QAM, the meshes are containing in the amplitude of the signal. Okay, so that's why its amplitude gain or power gain are being reduced. Okay, because of the distortion. But in FN and PM, we are not having these things in the meshes are in amplitude. Okay, that's why. Okay, got it? Any doubt till now?
No.
Okay. Okay, we can stop for today. We will see 1 dB compression and all those things tomorrow because these are the new topic. Okay.
Okay.
And we have the intermodulation product also, cross modulation. Okay, some more conceptual points are there in tomorrow class. Dual tone modulation and all those things. Okay, after that we can move to the PLL.
Okay.
Okay. Okay, then see you for tomorrow at the same time, right?
Yeah.
Okay.
See you. Thank you.
Okay. Okay. Bye. Thank you.